What's up, everybody? Welcome back. This is episode 3. I'm currently going through this college algebra final exam review. So this is the review that's given out by Texas State University's math department to all the college algebra students to help them review for their final exam. So I'm going through it in this video series question by question, and I'm currently on question number 47. So if you're looking for something before that, you can check my last 2 episodes, and if you're looking for something after that, then stay tuned. If for some reason you do not have a copy of this, it is in the description below. You can click it. There's a link to a PDF copy of this. If you're looking for a specific question, like number 62 or something, you can go below as well. There should be timestamps for all the questions that I'm covering in this video. I am putting time and effort into this. I hope to help as many people as I can. But if you do appreciate it, then let me know. Hit the like button, subscribe, and leave a comment below saying thank you for helping me out. That makes me feel really good when I see positive feedback. So without further ado, let's go ahead and get into it. We are on number 47, and it gives us 2 functions, and it says evaluate the function for the given value of x, okay? And what it wants us to evaluate is f minus g of 2. So this is actually a really easy problem. The only thing that's even a little bit tricky is just this notation and knowing what it means. And what this actually means is f of 2 minus g of 2, all right? These 2 things are actually the same thing. So that's the only thing tricky. And if this was a plus, it would be the same thing. It would be f of 2 plus g of 2. You could even have multiplication in here, f times g of 2, and it would be f of 2 times g of 2, right? So just pay attention to this notation, but other than that, it's pretty straightforward. We're plugging 2 into f and plugging 2 into g, and we're subtracting that f from that g, right? So let's see, let's plug 2 into f. So what is f of 2? We get 4. And then if I plug 2 into g, I get 1 over 2 minus 4. So let me see, minus 1 over 2 minus 4, and this should simplify to 1 over 2 minus 4. That's negative 2. So that simplifies to 1 over negative 2. So this becomes 4 minus 1 over negative 2. So really this negative in the bottom, I can bring it to the top either way. I can write it on the top or bottom or out front, right? So what this really is 4 minus negative 1/2. So I'm just going to make it 4 plus 1/2. And I could find a common denominator here if I want to write that as 8 over 2, or I could just say this is 4.5. But if you found a common denominator, then you would find that this is 9 over 2. All right, so for number 48, we are given this function. We are asked to find this expression, which is f of x plus h minus f of x all over h. So if you're going on to calculus, this expression will become very familiar. So it'll be used to find derivatives when we first learn about derivatives. But if not, we can still find this. We just have to evaluate it and simplify. So what is f of x plus h? And this is where most students get a little bit tripped up. What does this f of x plus h mean? Well, just a reminder, what if we have f of 2, right? Just a quick review. What does f of 2 mean? Well, that means I take my function, f, and I plug 2 in, all right? So when I plug 2 in, basically anywhere I see an x, I replace it with 2. So I have 2 squared minus 7 times 2, which comes out to be, let's see, 4 minus 14, that's negative 10. So f of 2 equals negative 10. So for f of x plus h, I do the same thing. X plus h is my input into my function f, all right? So anywhere I see an x, I replace it with x plus h, okay? So let me get rid of this real quick. That was just to refresh everybody on how this function notation works. So what is my f of x plus h? Well, let me write that off to the side here. F of x plus h is my function, but all the x's are replaced with x plus h. So I have x plus h squared, that's this part here, minus 7 times x plus h. Minus 7 times x plus h, all right? Now, since this is f of x plus h, I can just subtract f of x from this, and I'll have my numerator I need, right? So this is f of x plus h minus, what is f of x? Well, f of x is already given. It's my function in terms of x, right? So I have to subtract this entire f of x function. Be real careful with this part because a lot of students make mistakes. I have to subtract this entire function, which means I need my function to be in parentheses, right? Since I'm subtracting the entire function, I need to subtract both terms, which actually means my minus 7x is going to become a plus, right? That's why I need these parentheses. My negative will distribute to both. So be real careful with that part. On the bottom, I just have a lonely h down here. That's fine. Now I can evaluate this. So another common mistake is that students will distribute this squared. They'll write this is x squared plus h squared. No, you got to FOIL this out, right? This is x plus h times x plus h, right? X plus h times itself. That's what squared means. So I'm going to do that off to the side here. X plus h times x plus h. I trust that y'all can all FOIL, so I'll probably go through this pretty quickly. X times x, that's x squared. X times h, that's xh, but then I have plus x times h. So that comes out to be plus 2xh plus h squared. Hopefully y'all can see all the way over here. All right, x squared plus 2xh plus h squared is what this comes out to be. So that's this piece here once I've FOILed it out. So I'm going to go ahead and write that in here. The goal is I want to expand everything so I can combine all the like terms because I want to simplify this. This is technically the correct expression, but it needs to be simplified, right? Especially if the exam is multiple choice. You'll probably be looking at 4 choices right now that look nothing like this, right? So let's see, x squared plus 2xh, x squared plus 2xh plus h squared, minus this negative 7 distributes. So I have minus 7x minus 7h. Minus x squared plus 7x. Minus x squared plus 7x. This is crazy, but a lot of stuff will cancel here. It's pretty cool how this works. So I have a lonely h still on the bottom. So let's see, what all cancels? X squared minus x squared. Those are both gone. X squared is gone with the minus x squared. What else do I have? 7x minus 7x, right? A positive and a negative. Those are both gone. What else do I have here? I think that's it. I don't think anything else can cancel. I don't have any other like terms. So I have 2xh and h squared and a minus 7h all over h. So hopefully y'all can see all the way down here. This is 2xh plus h squared minus 7h all over h. And so what I can really do is I can factor an h out from the top and cancel with this h on the bottom. So I can actually get rid of my denominator completely and be left with something that's not a fraction. So if you want to think of it as canceling this h with each one of these terms, that's fine. But really what you're doing is you're factoring out an h and canceling. So I'll go ahead and write that step in because I think that's important. A lot of mistakes are made here with the canceling stuff. Students will do some crazy stuff trying to cancel. So I have 2x plus h minus 7 when I take this h out to front. And since this is all over h, these h's cancel, right? That's how I think of it. So my final expression is 2x plus h minus 7. All right, for this number 49, it says write the function in vertex form and determine the range. So for this function, to get it to vertex form, we need to do something called completing the square. And I do have a video on this where I go more in depth on my channel if you want to check that out. But to complete the square, the first thing we need whatever's in front of this x squared term to be 1, all right? So luckily, these share a common factor of 3. I can factor this 3 out. And once I factor the 3 out, I just have x squared plus 6x, right? And I can check that this is correct. If I put this 3 back in, I get right back to where I came from. This plus 35 is still chilling out there. Well, that's the first step, is you always want to make sure whatever's in front of the x squared is 1, okay? So second step, I look at this, what we call the b term, right? Whatever's the coefficient of the x, and I take half of this and I square it, okay? So if I take 6 over 2, I'll do some side work over here. 6 over 2, and I square it. Well, 6 over 2 is just 3. So this is 3 squared, which is 9. This is my number I need to be in here because, again, the goal for completing the square is I want to get this to be a perfect square trinomial so I can factor it into a binomial squared, right, and have it into my vertex form, basically. So I need to add a 9 inside here, all right? So what I get is 3x squared plus 6x plus 9. And again, you always take half of this x term, right? Half of this coefficient, square it, and that's what you're adding. So plus 35 is out here. So there's one issue is that my equation, I need to balance it, right? Because I can't just go adding stuff to one side of the equation. That changes the equation. I need to balance it. So sometimes you can add, if you add to one side, you can add to the other side. But what I think is better for this example is since we just have f of x on this side, this is just the function definition, is when I add in here, whatever I add in here, I subtract out here, right? Because if I add and subtract the same number, then I'm really just adding 0 to one side, which doesn't change the equation. That's okay to do. So that's what I'm going to do in this case, is I'm going to subtract, but I'm not going to subtract 9, right? Because think about what I actually added. This is the tricky part. It's a little bit tricky. I added 9 inside this parentheses, but there's a 3 out here being multiplied to everything. So what I really added is 9 times 3, right? So 27. This function got 27 units bigger from here to here. So I need to subtract 27 out here. That's the tricky part. It is a little bit tricky. You just got to be real careful, go step by step. So now this is a perfect square trinomial. This will factor nicely into a binomial squared. And that number that was b over 2 is always what's left inside here. So that b over 2 is 3. So we do have x plus 3 squared. So we have a 3 out here, x plus 3 squared, and this is plus 8, right? Because plus 35 minus 27 plus 8. And if you FOIL this out and distribute everything, combine like terms, you should get right back up to here. These two things are equivalent. So this is my f of x in vertex form. F of x in vertex form. So to find the range of this function, we need to think about what this function sort of looks like in terms of its graph. So this is obviously a parabola, so it's either going to open up or open down, right? If it opens up, then the range is from that y coordinate of the vertex all the way up to infinity. If it opens down, then the range is from negative infinity all the way up to the y coordinate of the vertex. So in this case, we know that it opens up since the leading term is positive, right? We know that it opens up. So we just really need to find the y coordinate of the vertex, and it will go from there all the way to infinity. That would be the range. So again, we know that our vertex is, let's see, what is the form of this? This is like x minus h, okay? So we have negative 3, and this is plus k out here, right? If you remember the general form, plus k, and this is like an a or something out here. So this is like the general form for vertex form, and our vertex is hk. So my vertex is at negative 3, 8. And remember, we're looking at the y coordinate because range has to do with the y values, all right? So from negative 8, that's where this y value is that corresponds with that bottom, the vertex, right? And since we're opening up, going all the way to infinity, our range is going to go from 8 all the way to infinity. All right? Hopefully that makes sense. All right, for number 50, we have a quick little word problem. It says the population P of T of a culture of bacteria is given by this function, P of T, where T is the time in hours since the culture was started. Determine the time at which the population is at a maximum, round to the nearest hour. So we're trying to find the time at which the population is at a maximum. So we know that this is a downward opening parabola because we have this negative out in front, right? This leading coefficient is a negative. So the time which we're at a maximum is going to be this x value, right? We could think of it as an x value. Technically, it's t, okay? Because this axis would be like our t axis, and this would be like the p of t's, right? Because p of t is kind of like our y in this case. T is kind of like our x. So we really need to find this x value, right? The x value of the vertex. So we use negative b over 2a, because negative b over 2a, if we have a parabola in this form, negative b over 2a will give you the x value of the vertex. So that's really all we need to do for this question here is negative 92,000 over 2 times negative 1,710. And this gives us, I think it's 26.9, but you round to the nearest hour. So 27 hours. And again, if it was asking for the maximum population, then we would have to take this time and go back and plug it into our function. So you have to be real careful what it's asking for. Make sure you read and understand what it's asking for. But for this problem, 27 hours. All right, number 51. A family wants to fence in a rectangular area for a garden. One side of the garden will border their house and will not be fenced. Find the dimensions of the garden with greatest area that can be enclosed with 40 feet of fencing. So for this kind of a problem, we could draw a picture. And again, anytime you see maximum, minimum, greatest, words like that, it should jump out to you that you're going to have some kind of a problem where you end up with a quadratic and you find the vertex, right? That's usually how these go. So if we have the side of a house is red like this, then we're building a garden. So the garden extends from the side of a house. Let's see if I can draw a rectangular coming out. So yeah, it's a rectangular shape. So we know that these lengths are the same because it's a rectangle. We can call these x and we can call this width y, right? It doesn't matter what you call them, what are we given? 40 feet of fencing, so that means this x plus y plus x equals 40, right? The total perimeter of these three sides. So we have x plus y. Well, that's the same as saying 2x plus y equals 40. Let's see, what else do we have? We are trying to find the dimensions of the garden with greatest area. So what is area? Well, area is x times y, right? Length times width. It doesn't matter that we're missing a side here. Whether this side is fence or house, the area is the same regardless. So we have area equals x times y, all right? So this is pretty much how all these word problems will go, where you're trying to maximize something, is that you'll have two equations, you'll do a substitution, and then you'll find the vertex. That's exactly how this is going to go. So I can do a substitution here. If I solve for y, I can solve for x, but I don't want to have to divide both sides by 2. I'll solve for y. So I'll draw an arrow down here, and basically I'm going to subtract 2x from both sides, and I get y equals 40 minus 2x, all right? Now I can substitute this y into this equation. So I have a equals x times y, which equals 40 minus 2x, right? 40 minus 2x. Now I'm going to be left with a quadratic where I can find the vertex, right? Because when I distribute this x in, what do I get? A equals 40x minus 2x squared. And if it looks better for you to switch those terms, then that's fine too, because then we know clearly what our a is. Our a is negative 2, and our b is positive 40. So we have a quadratic here. And this is a negative leading coefficient, so that means it opens down, which makes sense because we're going to have a maximum, right? So that makes sense. So again, I need to find the vertex of this. And once I take negative b over 2a, that will be the x-coordinate of the vertex. But let's make sure we're doing what it's asking us to do. Let's see, find the dimensions of the garden. So we want to find dimensions. So this x and y that makes this area a maximum, right? So this equation will tell us the maximum x, and then we can go back and plug that into probably this equation. We can plug in x to find the y, all right? So this negative b over 2a, that's negative 40 over 2 times negative 2, that's negative 4, that equals 10. That's our maximum x, right? That's the x, that's the length that gives us a maximum area. So I have a length of, I'll put L equals 10, right? This x equals 10. You can call it x too, it doesn't really matter. Let's call it x since we've been calling it x the whole problem. X equals 10. So if I substitute that back in here, I get y equals 40 minus 2 times 10, right? So y equals 20. And these are the dimensions, 10 and 20. These are the dimensions that give us a maximum area for this garden. All right, so for number 52, it says determine the end behavior of the graph of the function. So we're given this function. And finding the end behavior with a function like this, a polynomial, is actually really easy. You can do it just by looking at it. So I just went ahead and made some notes about end behavior. So again, when we have a polynomial like this, we want to look at the highest power term. That's going to tell us everything we need to know about the end behavior. So in this case, it's already in order from highest to lowest. So our highest power term is just right here. But if our highest power term has an even power and a positive coefficient, then our end behavior looks like this. So you'd say rises left, rises right, or up left, up right, however you want to call it. It looks like this. Even power, negative coefficient, falls left, falls right. Odd power, positive coefficient, falls left, rises right. Odd power, negative coefficient, rises left, falls right. So these are the 4 possibilities when dealing with these functions that are polynomials. And how I personally remember these is I just think of the basic functions, really. Even power, positive coefficient, I think of something like x squared, how it looks like a parabola and it opens up just like this. For this one, even power negative, I think of negative x squared, how it opens down like this. Odd power, positive coefficient, I think of x to the cube, just the most basic thing I can think of that looks like this, right? And then for this one, obviously, negative x cubed. So that's how I remember. I just remember what these kind of basic parent functions look like, and I'm able to remember how to determine the end behavior. But for this example, clearly we have an even power and a negative coefficient. So we're this falls left, falls right case. All right, for number 53, we are asked to find the zeros of this function and state their multiplicities. So the zeros of a function are the numbers that I can plug in for x that basically make this whole thing 0, right? That make y 0, if you want to think about it that way. So I can replace this f of x with 0, and I can solve for those x values, and those x values will be the zeros. And this should feel pretty familiar, because this is actually the same way that we find x-intercepts, right? We plug in 0 for y to find x-intercepts. So zeros are kind of like a fancy word for x-intercepts. The only difference that I've seen is that for zeros, we usually include complex zeros, right? That can't be represented on the real number line. And for x-intercepts, obviously, if it's a complex 0, then it's not an x-intercept, right? So that's the only difference I've seen. But really, we're going to replace this f of x with 0, and we need to fully factor this, all right? And that's where the multiplicities come into play, when we have this fully factored. The multiplicity is basically, the way I think of it, this isn't a formal definition, it's just the number of times that 0 appears whenever this polynomial is fully factored. And we'll see what that means in a second. First, let's fully factor this. So we have a common factor of x to the 4th, and I'm actually going to pull out a negative as well out front. That's usually what I do whenever I have a leading coefficient that's negative, and I'm factoring the common factor, I pull out the negative as well, just because it makes it easier to factor this part that's left. So what am I left with here? A positive 3x squared. And let's see, I pulled out a negative, so then this is going to be positive, and that's 2x. And now, since I pulled out a negative, this is going to be negative. Basically, everything changes sign, and that's just negative 5, all right? So I can factor a little bit further. I need to factor this trinomial, so I can use the AC method or the box method or something like that. For something like this, I'm going to personally use guess and check, just because I want this video to be, not be 3 hours long. So I'm going to use a little guess and check, and because these numbers aren't too bad. 3 is prime and negative 5 is prime, so it doesn't make it too bad. So since I have a 3x squared in the front, I know I either have x and 3x or 3x and x. So I'm just going to write my 3x here. And the only real thing I have to figure out is, right, I write the x here. Negative 5, I either have 5 and 1 or 1 and 5, and then I have to figure out whether it's plus, minus, or minus, plus, all right? So there's not really much guess and checking here. That's why I went to this method. So let's see. If I have I think the 5 might be here. Let me try this. That'll give me the 3x squared, the 3, the 5. I think this is going to work, because if I do minus 3 plus 5, does that get me back where I was? 3x squared minus 3 plus 5, that gives me the 2. Minus 3x plus 5x gives me the 2. And then minus 5, yeah, that's good. So now this is actually fully factored now, all right? And now I can use my zero product rule, which basically says that since I have 3 things here multiplied together that equal 0, that means I set this equal to 0, this equal to 0, and this equal to 0. And those will be my zeros, all right? And I have to remember when the multiplicities come into play that this is like to the first power and this is to the first power, okay? Because remember I said it's like the number of times that 0 appears. So if I set each piece equal to 0, I have negative x to the 4th equals 0. Obviously the answer is x equals 0, right, is the solution for x for this. So I do have a 0 of 0 with a multiplicity of 4, because I can expand this x out into x times x times x times x, right? It appears 4 times. That's how I think of it. So we do have a 0 of 0, and I'll put 0 with a multiplicity of 4. That's how I write it. I'll write the 0, and then I'll write a slash, and it's multiplicity. So all the solutions I'll write over there. Let's see, so what else? 3x plus 5, I can set that equal to 0. 3x plus 5 is equal to 0. And now I can solve for x, so I subtract 5 from both sides. And that gets me to 3x equals negative 5. And then I just divide both sides by 3. Divide both sides by 3, and I get to x equals negative 5 over 3, all right? And again, both of these zeros will have a multiplicity of 1. So I have x equals negative 5 over 3. That is a 0. And I write slash with a multiplicity, multiplicity of 1. And then my last 0, hopefully you can just see what this 0 is, right? If I plug in 1 here, it makes the whole thing 0. So when I set this equal to 0, I'll get x equals 1. So my last 0, I won't do the algebra on that one. Hopefully y'all can see that one. Is 1 with a multiplicity of 1. And in general, all your zeros, the multiplicities will add up to the highest power, all right? So since we do have x to the 6th out in front, all our multiplicities should add up to 6. So 4 plus 1 plus 1. That's a good check, but these are all the zeros and their multiplicities. All right, number 54, we're given another function and we're asked to do the same thing, find the zeros and the multiplicities. This is actually a lot easier because it's already fully factored for us. This is actually only a few steps to find this. Again, I'm going to replace this f of x with 0, but basically plug in 0 for y. And then since it's already factored, I can just set each piece equal to 0. And my multiplicities already jump out at me, right? So whatever 0 I get from this piece here, it's going to have a multiplicity of 6. This will have a multiplicity of 3, and this will have a multiplicity of 5. So if I set 4x cubed equal to 0, clearly if I, multiply both sides by 1/4, it goes away, and then I have x equals 0 pretty clearly, right? So I have x equals 0, this is 1, 0, and I'll write with a multiplicity of 3. Multiplicity of 3, all right? So that's my first 0 with its multiplicity. Second part, x minus 4 equals 0, so that means that x equals 4, right? If x minus 4 equals 0, then x equals 4 is a 0 with a multiplicity of 6, right? And then my last piece, you could probably see that x equals negative 3. I'll leave that algebra part up to y'all, with a multiplicity of 5. So this one's actually pretty straightforward. They did all the work for you pretty much. You just had to set each piece equal to 0 and identify the multiplicities. All right, for this number 55, it says use the factor theorem to determine if the given binomial is a factor of f of x. So we have this function, we have this binomial. We want to find out if this is a factor of this. So there are two main ways to do it, and they're essentially kind of the same thing, just slightly different ways of thinking about it. The first way, the most common way, is use synthetic division, because if this is truly a factor of this function, then if we take this function, if we take this polynomial and we divide it by this x minus 2, we'll get a remainder of 0. So we use synthetic division. If we get a remainder of 0, then we say, yes, this is a factor. If we don't, then we say, no, it's not. Okay, that's one way of thinking of it. Another way of thinking about it is that if this is truly a factor of this polynomial, then when I fully factor this down, x minus 2 will be basically a piece of that, right? Kind of like when we had with the last two examples, when we fully factored it down. So x minus 2 will be one of those pieces of this fully factored form, and that means when x equals 2, this becomes 0, and therefore the whole thing becomes 0, right? So if this is truly a factor of this polynomial, then when I plug 2 into this function, I should get 0. So those are two slightly different ways of thinking about it. More traditionally, we use synthetic division, so that's what I'm going to do. And again, I always use the root with synthetic division. So I put 2 out here, and I do this long little L thing, and then I put the coefficients. And if there's any gaps between, x squared and straight to the constant, I fill that in with a 0. So I have 2, 1, negative 13, negative 10. All right, and now I bring this down and I multiply 4, and then I add down, and then I multiply, that gives me 10, then I add down, then I multiply, then I add down. So this is my remainder, all right? And since my remainder is not 0, I know that this x minus 2 is not a factor of this function. All right, for number 56, we have determine the vertical asymptotes of the graph of the function. So when we're looking at vertical asymptotes, we're looking at what values for x can I plug in to make this denominator 0, right? Because if this denominator becomes 0, we have something that's undefined, so it can't be graphed. And then it's either a whole or an asymptote, okay? So really what we want to do is set this denominator equal to 0. And solve for x. And in order to do that, we have to fully factor the denominator. So I'm going to go ahead and start factoring. I'm actually just going to rewrite this whole thing. I'm going to write the x minus 9 up top. And on the bottom, I'm going to factor out a 2. We share a common factor of 2 between all these terms. So I'm going to factor a 2 out front. And I have x squared plus x minus 6. And the reason I'm not just taking this denominator aside here and setting it equal to 0 and factoring is because we could potentially have a whole instead of an asymptote. So a whole occurs if whenever I factor this, I get an x minus 9 and I can cancel with the top, then that 9, that x equals 9, right, that makes the denominator 0 is actually a whole and not an asymptote because we canceled it with the top, okay? So if your class hasn't taught that yet, then I apologize. And then you can just take the bottom and set it equal to 0. But this is what I like to do because, again, if it cancels, then it's just a hole. And this is kind of the difference. This is what a hole looks like. The graph just goes, and it just doesn't exist at one point. You have a little hole, right? For an asymptote, it does something like this. It's very dramatic. And we have something like this, right? And something like that, okay? So that's kind of the difference between hole and asymptote. But yeah, if it cancels with the top, then it's a hole. If it doesn't, then it's an asymptote. That's the general rule. So I'm going to finish factoring this guy. It shouldn't be too difficult. I factored out the 2, and now I think this will go down to plus 3 minus 2. I think that's what gives me what I need. So if I rewrite this one more time, and I can already see that x minus 9 isn't going to pop out, so I'm not really too worried about having a hole. But let's see, x plus 3, right? X minus 2. I'm not spending too much time on the factoring because hopefully y'all got that down. If not, I have like a ton of videos on factoring. So each one of these pieces I'll set equal to 0, and those will both be asymptotes just because we can't cancel out. If I had an x minus 9, again, that would be a hole, and just the remaining one would be an asymptote. But we have an asymptote at x equals negative 3 because that's what makes this x plus 3 equal to 0. And at x equals positive 2 because that's what makes this x minus 2 0, okay? So these are our 2 asymptotes of the graph of this function. All right, for this number 57, we are given this function and we are asked to identify the horizontal asymptotes. And if the graph does have a horizontal asymptote, determine the point where the graph crosses the horizontal asymptote. So I wrote out some notes just to review horizontal asymptotes. I figured this would be a good opportunity. So we have 3 cases, all right? And with horizontal asymptotes, we're only concerned with the leading term, okay? So we have 3 possibilities. Either the leading terms are the same power, which was what we have in this example, or the numerator's leading term is a higher power than the denominator's, or vice versa. The denominator's leading term is a higher power than the numerator. So I'm just going to do a quick review of all this. So again, when the leading term of the numerator is bigger than the denominators, we have no horizontal asymptote. And the best way I can explain this is that when we take things to power, squared, cubed, to the 4th, things are increasing very quickly, all right? And the best way for me to explain this is that x cubed just increases a lot faster than x squared. So as x gets bigger and bigger, the numerator is getting bigger a lot faster than the denominator. And what happens when we have a fraction and its numerator is increasing faster than its denominator? It's going toward infinity, right? The whole thing is getting bigger and bigger. This, we have the opposite thing going on, right? We have the numerators increasing a lot slower than the denominator. And think about what happens when the denominator increases faster than the numerator. We're getting closer and closer to 0. So this will have a horizontal asymptote at y equals 0. This will have no horizontal asymptote. And in fact, in the case where the top power is exactly 1 degree higher than the bottom, we'll actually have an oblique or a slant asymptote, if you've learned about those. So, but if it's like to the 4th over x squared, then there will be no slant or no horizontal asymptote, either of those. So now we have this case where we're looking at now. And again, we're not really concerned with the stuff afterwards because with horizontal asymptotes, we're looking at really, really big values or really, really small values of x, right? Think about plugging in like 10 billion for x, okay? So if I plug in 10 billion, the stuff after the leading term is pretty insignificant at that point, okay? And that's why we're only concerned with the leading terms. And this, so 4x squared over x squared, this will trend toward 4 over 1 because the x squareds will pretty much end up being the same thing. In fact, everything will kind of lead toward the same thing except this 4 over 1. So that's, hopefully I did a decent job of explaining it. That's how I was taught it and that's how I think of it. But when the powers are the same, in general, you take the leading coefficients. So 4 over 1. And if this were 3 over 5, then it would be 3 over 5. And that's what you do when the powers are the same. So we do have a horizontal asymptote at y equals 4. So horizontal asymptote at y equals 4. And now it wants us to find out if this graph does cross it and where that is at. So since it's at y equals 4, right, because horizontal asymptote is a horizontal line. That's why we do y equals, because it's a horizontal line. So I'm going to basically plug in 4 for y. I'm going to replace this f of x with a 4, all right? So let me erase what I got going on here and make some room for this work. All right, so I'm going to replace that f of x with 4. So I have 4 equals, then I have all this stuff still. 4x squared plus 6x minus 3 over x squared minus 8. So the best way to solve this, in my opinion, is get rid of the fraction. Multiply both sides by x squared minus 8. So I'm going to multiply this side by x squared minus 8, and that's going to get rid of the fraction and cancel this, right? And then I multiply this side by x squared minus 8, and that 4 will distribute. So now what I have here is 4x squared minus 8, 16, 20, minus 32. 4x squared minus 32. That's on the left side. And on the right side, I have 4x squared plus 6x minus 3. Nice. This is going to cancel out nicely. If I subtract 4x squared from both sides, minus 4x squared, minus 4x squared, those are gone. Now I have negative 32 on this left-hand side. And on the right side, I have 6x minus 3. So I can add 3 to both sides. Add 3. Then I get what? 6x, because these cancel. I get 6x equals, let's see, that's negative 29. 6x equals negative 29. So now solving for x, if I divide both sides by 6, I get x equals negative 29 over 6. Let me double check that that's correct. That is what I got. X equals negative 29 over 6. And ooh, if it wants the point, does it ask for the point? Determine the point. So we want the x comma y value. That's how we represent a point. So I'm going to erase this x equals, and I want to express it as a point. So this is my x value for my point, because that's what I just solved for. And the y value I know because that's what I plugged in. So this is the point where it crosses the horizontal asymptote. All right, number 58, find the asymptotes. So horizontal asymptotes and vertical asymptotes we are asked to find. So given this function, the first thing I'm going to do is find the horizontal asymptotes, because those I can just look at and use the rules that I know to find those. So again, since I have x over x, that means that my leading powers are the same, right? They both have the highest power of 1. So I take the leading coefficient, so negative 6 over 1. So my horizontal asymptote is at what? It's always y equals. Y equals negative 6 over 1. That's just negative 6, all right? So that's my horizontal asymptote. I didn't have to do any math to find that. Pretty cool, right? So vertical asymptote, again, I'm always looking at the denominator and what makes the denominator 0. So I'm going to take this x plus 9 and set it equal to 0. If I do that off to the side here, x plus 9 equals 0. Then I solve for x, and I get x equals negative 9, right, by subtracting 9 from both sides. So to confirm, you can go ahead and write vertical asymptote at x equals negative 9. But to confirm, it would be smart to factor this top, because again, it could be a hole. They could be throwing you a curveball, a trick question, giving you a hole and seeing if you recognize if it's a hole or an asymptote. So if you factored this top, you could like pull out a negative 6 or something, right? And then you'd be left with x minus 4. And then you can clearly see that nothing will cancel. But it's good to reassure yourself, because again, they could throw you a curveball like that. So vertical asymptote at, these are at symbols, by the way. I don't know why I use those for asymptotes. At x equals negative 9. So I have my asymptotes. We're good to go. All right, so for number 59, it says solve the inequality, write the solution set in interval notation. So we have this inequality here, and it's a quadratic. So quite a few problems back, we did some inequalities that were linear. This is a quadratic, so it's a little bit trickier. But we're still, for now, going to treat it as if it were an equal 0. So if this were equal 0, what would we do? We would factor this fully, right? So that's exactly what I'm going to do. And actually, before I try to factor it, I'm going to multiply both sides by negative 1, because I hate having negatives in the leading coefficient here. It messes me up when I'm trying to factor. That's just me personally. So if I multiply both sides by negative 1, I can get rid of that negative. X squared minus 4x minus 21. But I have to remember to do what? Flip the inequality, all right? So now that that negative is gone from out in front, I can factor it pretty easily. I'm looking for two numbers that multiply together to be negative 21 and add together to be negative 4. So I think those are negative 7 and positive 3. So I have minus 7 plus 3. So again, if this were equal 0, then my solutions would just be negative 3 and 7, all right? But this is less than or equal to 0. So how can I find out where this function is less than or equal to 0? So we have to think about the fact that this function is continuous, all right? And since this function is continuous, that means that I can put my pen down and I can draw the whole function without picking my pen back up. So that means in order to go from positive to negative or negative to positive, right, it has to cross through the x-axis. That's the only way to move from positive to negative or negative to positive. So that's how I use these zeros to my advantage is I mark down these zeros, which are -3 and 7, and then I think about, okay, well, if this is positive in this interval here, that means it's positive from -3 all the way to -infinity, right? Because it doesn't cross the x-axis again, and that's the only way for the function to change signs since it's continuous, okay? So really, I take 3 test values, and I plug in this interval, this interval, this interval, and I find out where it's positive, where it's negative, and then I use that to get my solution, okay? So I'm going to plug in -4. I get -4 plus 3, that's -1, that's a negative. -4 minus 7, that's a negative. So again, I don't need the actual number, I just need to know that it's 2 negatives which make a positive. I don't care about the actual number, so this isn't too bad. I can plug in 0. Any number in here will work. So 0, that's plus 3, that's a positive. 0 minus 7, that's a negative. So I have a negative in here, all right? So we're below the x-axis. And over here I can plug in 10, that's a positive, that's a positive. So I have a positive and a positive. So we're above, below, above, and since we're looking at where this is less than or equal to 0, I'm looking at this negative interval, and I'm going to include -3 because that's where it equals 0, and I'm going to include 7 because that's where it equals 0. So my solution in interval notation is -3, 7, including both -3 and 7. But that's the process. You want to get it down to its fully factored form. Set up a number line, put your zeros and test values around your zeros to see what intervals you're positive and what intervals you're negative. All right, number 60, we're doing the same thing. Solve the inequality, write the solution set in interval notation. So in this problem, most of the work is done for us. In fact, pretty much all the work is. We have it in a fully factored form so we can identify the zeros and we can set up our number line and find out where this function's positive, where it's negative, and get our solution from that. So what are our zeros? Let's see, I can set -3x equal to 0. So I have x equals 0 as one of my zeros. X plus 3, I can set that equal to 0. And I have x equals -3, that's one of my zeros. I trust that y'all can find zeros, that's why I'm just kind of writing these out. And then I have x equals 4, all right? I set basically each one of these pieces equal to 0. So now I draw my number line here, and I can graph these things. I have -3. I guess I'm not really graphing, I'm just kind of, I can plot them on here. So 0, 4. And now I want to test all these intervals so I can get my solution. So 1, 2, 3, 4 different intervals. So I'm going to try -4 here. I get -3 times -4, that's a positive. -4, oh wait, this is squared. So no matter what I plug into this thing, it's going to be squared. So this is always positive. So notice that, it might save you some time. I don't have to worry about that, it's always positive. So again, -4 times -3, that's a positive. 4 minus -4, that's a positive. So I have a positive over here. Okay, so then what about -2? I have a negative here. Let's see, no, a positive. A positive there because -3 times -2, that's a positive. 4 minus -2, that's a positive again, which makes sense because if we know anything about multiplicities, we know that an even multiplicity means that that 0 is just going to touch and bounce back up. So that's pretty cool because it lines up with what we already know about graphing polynomials. Let me test like 2. So I get, this is a negative. -3 times 2, that's a negative. 4 minus 2, that's a positive. So I get a negative here, which makes sense because here I have an odd multiplicity, and I have an odd multiplicity with this as well. So I can guess that this is going to be positive, but I'll double check. I'll plug in 5. I get a negative here, and I get a negative here that becomes a positive. So I've confirmed my suspicion that this interval is positive. So now I can get my solution from here in interval notation, but I got to be real careful because there's one easy mistake I can make, and I can say positive, positive, and I can write from -infinity to 0. But again, remember that at -3, this thing equals 0, and I want to know when it's greater than 0. So I do not want to include this 0 in my solution. So I'm going from -infinity all the way up to -3, union, and then I'm starting back up at -3 and going to 0, union, and then I'm starting back up at 4 and going all the way to infinity. So this full thing is my solution, and be careful with that mistake. It's easy to make. Always be careful and pay attention to whether you are greater than or equal to or strictly greater than. But yeah, this is the interval for my solution set. All right, so number 61, we are given a graph and asked to solve the inequality. F of x is greater than or equal to 0. I don't expect anyone to really have trouble with this. You pretty much just look at the graph and see where is this function greater than or equal to 0, all right? So we're going from -infinity, we're including -2 since it's greater than or equal to, and we're including 4, all right? So our solution set in interval notation is -infinity all the way to 4, including 4, because we are greater than or equal to. All right, for number 62, it says solve the inequality, write the solution set in interval notation. So this is yet another inequality, but this time it is what we call a rational inequality. So I'll be honest, these are pretty tricky. I'm going to do my best at explaining this. But the reason it's tricky is because remember when I said in order for a function to go from negative to positive or positive to negative, it had to cross the x-axis, right? It had to cross through 0. Well, the problem is that's only for functions that are continuous. And what we have here is clearly an asymptote when m equals 9, all right? And the problem with asymptotes is that you can have stuff happen like this. If that's the x-axis, this is the y-axis, you can have functions that look like this, right? They go from positive to negative because of this asymptote. It can jump without ever actually crossing through the x-axis, okay? So in general, whenever we set up our number line for these rational inequalities, we're going to have our zeros on here, but we're also going to have any asymptotes on here. We're going to have to check those intervals as well. So use those asymptotes as sort of partitions to check intervals as well. That's the only difference. But what I like to do, and if your instructor has a better way to do this, then please do it that way. It's honestly been a little bit since I've done rational inequalities, but what I like to do is get 0 on one side. So I'm going to subtract minus 2 on both sides. So I have 3 over m minus 9 minus 2 is greater than or equal to 0. And I'm going to draw an arrow here between steps because my next step is going to be common denominator, m minus 9, right? So I can multiply 2 by m minus 9 over m minus 9. So over here I have 3 over m minus 9 minus 2 times m minus 9 over m minus 9, all right? And this is greater than or equal to 0 still. Hopefully I can see all the way over here. All right, so my next step, again, I'm going to combine these because now I have a common denominator, and I'm actually going to distribute this negative 2 as well in one step. I think I can handle 2 steps at once. So if I combine these, I get 3 minus 2m, and this becomes plus 18 because I have minus 2 times negative 9. That's plus 18 all over m minus 9. And this is still greater than or equal to 0. So now I have one more arrow because I'm going to combine my like terms. So I have 21 minus 2m. And this is over m minus 9. And this is greater than or equal to 0. So now I have everything I need. I have it combined into one rational expression here to where I can get my number line now. I can do my number line. And I can put my asymptote as well as my 0 on here. So I know my asymptote is 9 because that still jumps out at me. But I need to find my 0. So I basically need to set this 21 minus 2m equal to 0 and solve. So 21 minus 2m equal to 0. So add 2m to both sides. I get 21 equals 2m. And then if I divide both sides by 2, I get m equals 21 over 2. So that is approximately 10, oh, it is 10.5, exactly, not approximately. 10.5, whoops, I'll write it as 21 over 2. I'm going to write what, I just wanted to find out what it was with respect to 9, right, whether it was left or right. That's the only reason I cared about 10.5. So now I have my intervals. I'm going to plug in 8 and see what that gets me. And again, I'm working with this guy here. This is the main guy we're worried about. So if I plug in 8, I get 21 minus 16, that's a positive on top. 8 minus 9, that's a negative on bottom. So this is a negative, all right? Let's see, what if I plug in 10? I get 21 minus 20, that's a positive. 10 minus 9, that's a positive. So I do have a positive here. What if I plug in anything past that? Let's see, I plug in 20, all right? So 21 minus 40, that's a negative. 20 minus 9, that's a positive. So I have a negative here. So my solution is this interval. But the only thing I have to pay attention to, this is a common mistake made, is that since this is an asymptote, I always have this open parentheses, right? I always have this open parentheses because this function will never actually get to 9. It's an asymptote. It's undefined at 9, but it's going to keep approaching it, right, if that makes sense. So again, I have this closed bracket here at 21 over 2, but I have an open parentheses at 9. So my final solution, I'll write it all the way up here, is 9, whoops, sorry about that, 9 comma 21 over 2, and this has the bracket. So hopefully that explanation wasn't too crazy. Again, it's a little bit tricky, but hopefully this made sense. All right, for number 63, it gives us a graph, and it asks us to solve the inequality when f of x is strictly greater than 0. So we have f of x greater than 0. So I drew this the best I could. You know, this is 2, this is 3. So we can clearly see that this part down here is not greater than 0. We're not really worried about that. We can see that it is greater than 0 between 2 and 3, and that's actually our solution here, is from 2 to 3. And the reason why we don't include 3 is because we're strictly greater than, not greater than or equal to. And the reason we don't include 2 is because that's an asymptote. The function never actually, right, at 2, it's not actually defined. But from 2 all the way to 3, if we're not including those boundaries, it is greater than 0. So a little bit tricky because we're just looking at a graph here, but hopefully that makes sense on why you don't include 2 or 3. All right, number 64, a one-to-one function is given, right? An expression for the inverse function. So I go pretty in-depth into inverse functions on a video on my channel if you want to go check that out. But yeah, I break it down into steps. So step 1, I always replace f of x with y just because the notation is better, it's cleaner, easier to deal with. So y equals 5 minus x over 7. That's my first step. Second step, switch the position of x and y. So anywhere I see a y, I replace it with x. Wherever I see an x, I replace it with y. All right, third step, solve for y. All right, so I want to get y equals something. So solving for y, I'm going to multiply both sides by 7. So I got 7 here, 7, those cancel. So I'm going to rewrite this down here. I have 7x equals 5 minus y. All right. Again, I'm solving for y, so I could add y to both sides, or I could subtract 5 and then multiply by -1. I'm going to do that. I'm going to subtract 5 from both sides. Draw an arrow here. I always draw an arrow between steps, by the way, if you're wondering what all these arrows are, just to make it clear that, like, here's another step, you know what I mean? So 7x minus 5, those 5's cancel, equals -y. Now I'm going to multiply both sides by -1. So I have -1 going to this whole thing, -1 going to this, which gives me just y, right? I have just y equals, -1 goes to here, so -7x plus 5, or I could write this as 5 minus 7x as well if I switch those. And my last step is always to replace y with the inverse notation, just because it's pretty, and yeah, we found the inverse, so we want to use our fancy inverse notation here. All right, so inverse notation equals -7x plus 5. How could you check your answer? Well, you could take that function, plug it in here, you should just get out x, or vice versa, all right? But you shouldn't need to do that as long as you follow these steps correctly. So here's our inverse function. All right, for number 65, I'm given another function and asked to find the inverse of this function as well. So step 1, same thing, I replace f of x with y. Let's get this into a better notation. All right, so I have x plus 3 over x plus 8, that's what y equals. What's my step 2? Switch the position of x and y. So I'm replacing all my y's with x, and I'm replacing all my x's with y. So I actually have 2 y's. This example is a little bit tricky, all right? So since I have 2 y's, what's going to end up happening is I want to get everything with y on one side of the equation by itself and everything else on the other side. So if all my y terms are on one side, I can factor out a y, and I can divide by whatever's remaining, divide both sides. So we'll see how that works when I do it. I'm going to multiply both sides by y plus 8. Let's go ahead and get rid of this fraction here. Multiplying both sides by y plus 8. The fraction's gone, so now I have y plus 8 times x equals y plus 3. So I want to distribute this x. So my next step here, I have x times y, and you could write it as yx too, same thing, plus 8x. Let's see, make sure that's right. X times y plus 8x equals y plus 3, equals y plus 3. All right, so now my y terms are xy and y. So I'm going to subtract the y over to this side because I want both my y terms by themselves on one side of the equation. And I want to subtract my 8x over to here. So I'm going to subtract both sides by y first. Subtract both sides by y, and I get xy plus 8x minus y equals 3, all right? So now I'm going to subtract both sides, 8x from both sides. I probably could have done both of those in one step. You probably could have done that, that's fine. So my 8x is canceled there. I have xy minus y, xy minus y equals negative 8x plus 3, or 3 minus 8x, either way. So equals, all right, 3 minus 8x, okay? So now again, I have all my y terms on one side of the equation by themselves, so I'm going to factor the y out in front. So what happens when I factor the y out in front? I get y, and what am I left with? X there minus just 1, right? and this equals 3 minus 8x. Now all I have to do is divide both sides by x minus 1. So my final solution for y is y equals 3 minus 8x divided by x minus 1. And what's the last step I do is I replace that y. I'm going to erase that y and replace it with my inverse notation, f inverse of x. And if I want to check my answer, I can take this f of x and plug that into both my x's. It would be quite tedious, but you can check your answer. You should just get x when you evaluate that. But this is my inverse function. All right, for number 66, you really don't have to do any computations or any math. It just wants you to remember the relationship between a function and its inverse. And that is that the domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. So for our solution for the f inverse here, the domain will simply just be the range of the original function, which is from -9 to infinity, and then the range will just be the domain of the original function, which is from -6 to 1. All right, so for number 67, we are asked to write the parent function and identify all the transformations in order. So our parent function, hopefully that's clear. We can write our parent function is square root of x. So f of x equals square root of x is our parent function. And we can see that 3 transformations are being applied. We have a, let's see, horizontal shift. This is to the right, 4.5 units. We have a vertical compression by a factor of 1/2, right? We're vertically compressing. And then we're shifting up 6.6 units. So the order of these, all right, because we need to have 1, 2, 3. We need to list these in order. So the order, let's see, maybe I can write the general form. Maybe this will help. I always think of working from the inside out as far as the order. So if we have something like this, f of x equals a, this is the vertical stretch or compression. And then we have square root, and you could replace the square root with the parentheses and squared, and the order is still the same, right? Just a different parent function. So if we have some b here, that is a horizontal stretch or compression. And then we have something in here where we have x minus c, and this shifts horizontally, all right? And then outside of here, we have this plus d, all right? And this shifts vertically up and down. So again, I always think of working from the inside out. So first, this horizontal shift, and then this horizontal stretch or compression. And then third, we have this vertical stretch or compression, then we have the vertical shift. So that's the order. So the first thing that's going to affect this is the shift to the right. So I'm going to say right, shift to the right, 4.5. And I'm just using shorthand here because I don't want to write full sentences, take forever. Let's see, this is going to be a vertical compression by a factor of 1/2. You could write that full part out if you want. Vertical compression by a factor of 1/2. And then shift up. So you're shifting up 6.6 units. So this is the order. We go shift to the right, compress, shift up, and our parent function is f of x equals square root of x. All right, so for this number 68, we are asked to solve this equation, and this is an exponential equation, and I have plenty of videos on exponential and log equations on my channel if you want to go watch those and check them out. So for this equation, well, there are 2 main ways we solve exponential equations. One, we use logarithms, right? Because logarithm is the inverse of exponential. We can use logarithms, and we can bring the variables down from the exponents out in front so we can solve them, right? The second way is kind of a clever way, and that's only if we can get the exponential to look something like this. If we can get something like a to the x equals a to the y, where we have the same base, then we can say that, okay, that means x must equal y, all right? So for this example, I think we can get it to look like this, to have the same base, because I think I can write 64 as 4 to some power. So that's usually what you want to kind of look for in the beginning, be like, can I make these bases look the same? And if you immediately notice then you can't, then go start using logarithms to solve. But if you can, then it makes it a lot easier than using logarithms. So I have to think, what 4 to what power is 1 over 64? That may be tricky to think about, but I think 4 to the 3rd power is 64. All right? 4 times 4, 16 times 4, yeah, that's 64. So what if I wrote 1 over 4 to the 3rd? Or another way to think of that is 4 to the negative 3rd, right? So I can replace this 1 over 64 as 4 to the negative 3rd. So that's exactly what I'm going to do here. I'm going to keep that there, but I'm going to keep that separate. So let's see, I have 4 to the 3x plus 3. And that equals, let's see, this is 4 to the negative 3rd. 4 to the negative 3rd, and this is still to the x minus 9 power. So I'm going to erase this sort of scratch work here. And now I really got to think of my exponent rules. I got to make sure I do the right thing here because I have a power to a power, so I need to multiply this -3 all the way through to the x and to the -9, all right? So if I rewrite this, I can rewrite it as I still have the 4 to the 3x plus 3, right? Because I don't quite have the same base yet. This is 4, but this is a base of 4 to the -3rd. I need it to just be 4 and 4, and that's why I need to distribute this -3, multiply it through. So I can just have 4 down here. And up top I can have -3x, so that's -3x. And then negative times a negative, that's going to become a positive, plus 27. All right, 9 times 3 plus 27. So now I have the same base, so I can say that means this equals this. So I can set this up to where 3x plus 3 equals -3x plus 27. And now this is a simple linear equation that I can solve. See how much easier that was than having to deal with logarithms? So again, you could have taken log of both sides and used your calculator. Maybe you could have taken log base 4 or something like that. That would have worked. But we always want to use this method when we can because it's a lot more convenient, as you can see. So I'm going to add 6x to both sides. I'm sorry, add 3x. I was jumping ahead because I know that's going to give me 6x. So add 3x to both sides plus 3x. If I cross these out, I have 6x plus 3. 6x plus 3 equals 27. Now I subtract 3 from both sides. All right, -3 minus 3. If I draw an arrow over here, I have 6x equals 24. And now I can divide both sides by 6, and I have x equals 4, right? 24 divided by 6 equals 4. So x equals 4 is my solution. I'm going to write it up here. X equals 4. All right, for this number 69, we are given this exponential function with a word problem. And this is actually pretty straightforward. It just wants to make sure we know how to evaluate an exponential function. So we have the atmospheric pressure on an object decreases as altitude increases. If A is the height in kilometers above sea level, then the pressure PA is approximated by this function. Determine the atmospheric pressure at 5.458 kilometers. So again, 5.48 kilometers, that's my A. So all I'm doing is plugging 5.48 into A and really punching that in a calculator, right? So I have P of 5.48 equals 760 times e to the -0.13 times 5.48. And when I punch this in a calculator, I get 16.3 million. And it says round to the nearest 100,000. So that's what I get after I round. So 16.3 million. But yeah, this is pretty straightforward. As long as you really know how to use a calculator, you should be good. All right, for this number 70, I am solving this logarithmic equation. And again, if you want to see this in depth, go check my channel. I have lots of videos on this. So for this logarithmic equation, I really want to get log something equals some number, right? That's the goal. So I really need to combine these two logarithms, which I can do if I know my logarithm properties, all right? So since I have a minus here, I can combine them, and it's going to become division inside a single logarithm. So once I combine them, I get log base 2. And inside here is going to be 64x over x plus 77, right? The first one always ends up in the numerator, the second one in the denominator, and this equals 3. So now I can use my property that allows me to transform this into an exponential, right? I can say this is the same as saying 2 to the third equals this stuff inside here. That's why I remember it. I draw the arrows. 2 to the third equals that stuff. So 2 to the third is 8. So I have 8 equals this stuff inside the log, 64x over x plus 77. These are kind of ugly numbers. These are kind of big because now I got to multiply both sides by the denominator. I want to get rid of that fraction. So I'm going to multiply both sides by x plus 77. All right, if I do that to both sides, x plus 77, then that cancels the denominator. That's exactly what I wanted. Now I got to distribute this 8. So let's see, I get 8. Let me check because I wrote this down earlier. 8 times 77 is 616. So I end up with, I'll write it down here, 8x plus 616, and this still equals 64x, all right? So now if I subtract 8x from both sides, minus 8x, what do I end up with? 64 minus 8, that gives me 56x So I get 56x equals 616. And if I divide both sides by 56, divide by 56, then I get x equals 11. So whenever you get answers with logarithms, you want to go back in and make sure they work. For these, they do work. But again, remember, our domain for logarithms, we have to be greater than or equal to 0. So we can't have negatives inside of logarithms. You won't really see that with this kind of example, but for future examples, we will see that. But it's always a good habit to check. Go plug it back in, make sure it works. But yeah. All right, I think this is a good stopping place. So make sure to subscribe and stay tuned for part 4. But if you are enjoying this, if you enjoyed this video, make sure to hit like. If you have questions, leave comments below and leave any positive feedback. If you do appreciate the videos, if they're helping you, let me know in the comments below. Until next time, keep flexing those brain muscles, and I'll see you on the next video.